Today we will continue the lecture with solved examples on inverse trigonometric functions, derivatives of inverse trigonometric functions. In that, the next example is differentiate the following with respect to x, and the example is sine inverse of 2x upon 1 plus x square. So let y is equal to sine inverse of 2x upon 1 plus x square. Now here this 2x upon 1 plus x square, it looks like 2 tan theta upon 1 plus tan square theta. So we will substitute this x is equal to tan theta. So theta is equal to tan inverse of x. After putting x is equal to tan theta in the equation, our equation becomes y is equal to sine inverse of 2 tan theta upon 1 plus tan square theta. But it's nothing but sine 2 theta. So sine inverse of sine of 2 theta is same as 2 theta, but theta is tan inverse of x, so we get y is equal to 2 times tan inverse of x. So we differentiate this function with respect to x. So dy by dx is equal to 2 is a constant, so we can keep it outside the derivative. D by dx of tan inverse of x, and the derivative of tan inverse of x is 1 upon 1 plus x square. So 2 into 1 upon 1 plus x square is the derivative of the given function. Now the second problem is cos inverse of 2x in bracket 1 minus x square. Now again it looks like whenever there is 1 under root 1 minus x square, we will put x is equal to cos theta or x is equal to sin theta. Both will work here. So we put x is equal to sin theta. So theta is equal to sin inverse of x. After putting x is equal to sin theta in this expression, 2 times sin theta under root 1 minus sin square theta. But 1 minus sin square theta is cos square theta. This root and this square will cancel to each other and we get 2 sin theta cos theta. But 2 sin theta cos theta is nothing but sin 2 theta. So now here there is cos inverse and we get sine. So here you have to use the allied angle formula, so that cos of 90 minus theta is sine theta. So now we get cos inverse and cos, so cancel each other and we get, by using the property of the inverse trigonometric function, y is equal to pi by 2 minus 2 theta. So theta is equal to sine inverse of x. We put that value here and then differentiate with respect to x. So here d by dx of pi by 2 minus d by dx of this 2 sine inverse x. Pi by 2 is a constant, its derivative is 0. 2 is constant and derivative of sine inverse of x is 1 upon square root 1 minus x square. So we get dy by dx is equal to minus 2 under root 1 minus x square. Differentiate the following with respect to x. Cosec inverse of 1 upon 3x minus 4x cube. It is given. So let y is equal to the given function cosec inverse of 1 upon 3x minus 4x cube. Now we have one property from the inverse trigonometric functions or trigonometric functions, that the cosec inverse of 1 upon x is nothing but sine inverse of x, or sine inverse of x is cosec inverse of 1 upon x. So using that property, I write y is equal to sine inverse of 3x minus 4x cube. Now here 3x minus 4x cube, it looks like 3 sine theta minus 4 sine cube theta is nothing but sine 3 theta. So I put x is equal to sine theta. So theta is equal to sine inverse of x. So I get y is equal to sine inverse of 3 sine theta minus 4 sine cube theta. This bracket entry or bracketed function is nothing but the value of sine 3 theta. So sine inverse and sine will cancel to each other and we get again y is equal to 3 theta, but theta is sine inverse of x, so y is equal to 3 sine inverse x. Differentiate with respect to x. 3 is constant, we can take outside, and derivative of sine inverse of x is 1 upon root 1 minus x square. So 3 upon root 1 minus x square is the derivative of the given function. Again, differentiate the following with respect to x. Tan inverse of 2 e raised to x upon 1 minus e raised to 2x. Again, it looks like in the 2 times tan theta minus 1 minus tan square theta. because we have to think of the double angle formula of tan. So let y is equal to the given expression. So put e raised to x is tan theta. So theta is equal to tan inverse of e raised to x. After putting the value and simplifying, we get y is equal to 2 theta. That means y is equal to 2 tan inverse of e raised to x. Now differentiate it with respect to x. 2 is constant and tan inverse of f of x. Tan inverse of f of x. Its derivative is 1 upon 1 plus f of x square into f dash of x. So 2 upon 1 plus e raised to x bracket square into d by dx of e raised to x. But d by dx of e raised to x is e raised to x. So we get 2 e raised to x upon 1 plus e raised to 2x. Now, cos inverse of 1 minus 9x square upon 1 plus 9x square. You have to differentiate with respect to x. So let y is equal to the given function. Uh, we rewrite this function, simplify it as 1 minus 3x bracket square upon 1 plus 3x bracket square. Now, if here there is a cos inverse function is there. So in bracket we must have the cos 2 theta, cos 3 theta, or sin theta, sin 3 theta, and so on. But the expression in the bracket is look like 1 minus something square upon 1 plus something square. So we put 3x is equal to tan theta. So theta is equal to tan inverse of 3x. Now 1 minus tan square theta upon 1 plus tan square theta is nothing but cos 2 theta. So using the property we get 2 theta. Cos inverse of cos theta is theta. So y is equal to 2 tan inverse of 3x. Differentiate with respect to x. 2 as it is, tan inverse of f of x is 1 upon 1 plus f of x square into f dash of x. So what is dy by dx? It is 6 upon 1 plus 9x square. Next example, cos inverse of 2 raised to x minus 2 raised to minus x upon 2 raised to x plus 2 raised to minus x. Again it is same as this that of this example, but we have to just convert the given problem into this 1 minus something and 1 plus something, and how to convert it into that form. Y is equal to cos inverse of multiplied by 2 raised to x. If you multiply numerator by 2 raised to x, then we get 2 raised to 2x minus 2 raised to minus x into 2 raised to x is 2 raised to 0 is 1. Similarly, multiply denominator also by 2 raised to x. So 2 raised to x into 2 raised to x is 2 raised to 2x plus 1. Again we simplify it by taking minus 1 common, and 1 minus 2 raised to x bracket square upon 1 plus 2 raised to x bracket square, and then we substitute 2 raised to x is equal to tan theta, so that theta is equal to tan inverse of 2x. Now after putting or using this substitution, we get y is equal to cos inverse of minus 1 in bracket 1 minus tan square theta upon 1 plus tan square theta. It is nothing but cos 2 theta. So put this value of cos 2 theta, we get y is equal to cos inverse of minus cos 2 theta. That means y is equal to cos inverse of cos pi minus 2 theta, because cos pi minus theta is nothing but minus cos theta. So we are not changing anything here. We are just getting take care of this minus 1 minus sign, and which is equal to this, using the property of cos inverse of cos theta is equal to theta, we get pi minus 2 theta. Here we put the value of theta as tan inverse of 2x. So and then we differentiate with respect to x. Y is equal to, or dy by dx is equal to dy by dx of this pi minus 2 times dy by dx of tan inverse of 2 raised to x. Pi is a constant, so its derivative is 0. 2 is as it is. Derivative of tan inverse of f of x is 1 upon 1 plus f of x square into d by dx of this f of x. So its derivative is 2 raised to x log 2. Now after putting this value, we get this equation of simplifying 2 and 2 raised to 1 and 2 raised to x is 2 raised to x plus 1. And here there is 2 raised to x bracket square is 2 raised to 2x. Differentiate the following with respect to x. tan inverse of square root 3 minus x upon 3 plus x. Now here x is equal to 3 cos 2 theta because there is 3 and not 1. If there is 1, then our substitution may be like this: x is equal to only cos 2 theta. But because of this 3, we have to take x is equal to 3 cos 2 theta. Just go through the standard substitution which are given in the last lecture. So here theta is equal to 1 upon 2 cos inverse of x by 3. So put x is equal to 3 cos 2 theta in the example. Take 3 common, they will cancel to each other, and 1 minus cos 2 theta is 2 sin square theta. 1 plus cos 2 theta is 2 cos square theta. Again here 2 will get cancelled. Sin square upon cos square is tan square, and due to the square root and the square, they will cancel to each other and we get tan theta. Again tan inverse of tan theta is theta. Using that property, we get y is equal to theta. Theta is equal to 1 upon 2 cos inverse of x upon 3. We will differentiate this equation with respect to x. So 1 upon 2 is a constant. Derivative of cos inverse of f of x is minus 1 upon under root 1 minus f of x square into f dash of x. But 1 upon 3 is constant. So here there will be only derivative of x. It is 1. So 1 upon 3. Then just simplify it. You get the required answer. Differentiate the following with respect to x. Sin inverse of 5 root 1 minus x square minus 12x upon 13. Let y is equal to the given expression. Then we will put, as there is root 1 minus x square, so we put x is equal to sin theta or x is equal to cos theta. Here I am using x is equal to sin theta. So theta is equal to sin inverse of x. So y is equal to sin inverse of 5 under root 1 minus sin square theta minus 12 sin theta upon 13. So 1 minus sin square theta is cos square theta and its root is cos theta. So we get sin inverse of 5 cos theta minus 12 sin theta upon 13. So now we will divide the numerator separately by 13. 5 upon 13 cos theta minus 12 upon 13 sin theta. So now here there is a sin inverse. So in bracket I must get sin a plus b or sin a minus b. There is no harm if we get cos a plus b or cos a minus b. Only we have to use the allied angle formula there. So if we got the expression in terms of sine, then we will not have to use the any allied angle formula. Now let put 5 upon 13 equal to sin alpha and 12 upon 13 is equal to cos alpha. Then just check whether these two satisfies the first fundamental identity, sin square alpha plus cos square alpha is equal to 1 or not. Definitely their square and addition will be 1. So tan alpha is equal to sin alpha upon cos alpha. After taking their division, you get pi upon 5 upon 12. So alpha is equal to tan inverse of 5 upon 12. So our given expression y is equal to sin inverse of sin alpha cos theta minus cos alpha sin theta. But it's nothing but sin of a minus b, sin alpha minus theta. Now using the property of inverse trigonometric function, this will cancel to each other and we get alpha minus theta. So y is equal to alpha minus theta. Hence tan inverse of 5 upon 12 minus sin inverse of x. So we differentiate this expression with respect to x. This is the constant. There is no x in this first term, so its derivative is 0. Now minus as it is, and d by dx of the sin inverse of x, its derivative is 1 upon under root 1 minus x square. So simplifying it, we get the derivative minus 1 upon root 1 minus x square. Next example, sin inverse of 2 raised to x plus 1 upon 1 plus 4 raised to x. So let y is equal to sin inverse of 2 raised to x plus 1 upon 1 plus 4 raised to x. Now what we will do here, this 2 raised to x plus 1 using laws of indices, I will write it as 2 times 2 raised to x. And this 4 I will write 2 square. So what we get? Sin inverse of 2 into 2 raised to x upon 1 plus 2 raised to x bracket square, and then we will use the substitution 2 raised to x is equal to tan theta. So theta is equal to tan inverse of 2 raised to x. So 2 tan theta upon 1 plus tan square theta is nothing but sine 2 theta. So this will two cancel to each other, and then we get 2 theta. But theta is tan inverse of 2 raised to x, and then we will differentiate this with respect to x. So using the differentiation, dy dx of tan inverse of f of x is 1 upon 1 plus f of x square into f dash of x. So dy dx of 2 raised to x. Now what is the derivative of a raised to x? Derivative of a raised to x is a raised to x log a. So 2 upon 1 plus 2 raised to bracket square into 2 raised to x log 2. Again, these 2 and these 2 will combine, we get 2 raised to 2x plus 1 log 2 as it is. 1 upon 1 plus 2 raised to x its square is nothing but 2 raised to x square, or we can simply write 1 plus 2 4 raised to x. Differentiate with respect to x. Tan inverse of 4x upon 1 plus 21 x square. So let y is equal to tan inverse of 4x upon 1 plus 21x square. So I will write this 4x as 7x minus 3x. Why I have chosen here 7x and 3x? Because here I am going to choose two functions such that their difference is 4x and their multiplication is 21x square. Okay, so we are using the tan inverse of x minus y upon 1 plus xy, that property from inverse trigonometric functions. So we get tan inverse of 7x minus tan inverse of 3x. We differentiate this function with respect to x. D by dx of the first tan inverse of 7x minus d by dx of the second function tan inverse of 3x. So tan inverse of f of x is 1 upon 1 plus f of x square into d by dx of f of x. Using that formula, we come to the answer 7 upon 1 plus 7x square minus 3 upon 1 plus 3x square. Now the next example, 7x upon 1 minus 12x square. Now similar to this, the previous one, we have to search two functions whose sum is 7x and whose product is 12x square. So here there are two functions, 4x and 3x, whose sum is 7x and whose product is 12x square. So again I will use the property tan inverse of x plus y upon 1 minus xy as tan inverse of x plus tan inverse of y, and then I will differentiate with respect to x. So tan inverse of 4x its derivative plus tan inverse of 3x its derivative. Tan inverse of 4x 1 upon 1 plus 4x square into d by dx of 4x. Similarly for the other function, so we get here derivative of 4x is 4, so 4 upon 1 plus 4x bracket square plus 3 upon 1 plus 3x bracket square. Cot inverse and bracket b minus sin x minus a cos x upon a sin x plus b cos x. Now we know that cot inverse of x is same as tan inverse of 1 upon x, or tan inverse of x is cot inverse of 1 upon x. So using that in property, we can write the given problem. Instead of cot inverse, I will write tan inverse. Now in next step, I will take something common from this. What I will take common? I will take common sin x or a sin x. I will take the common a sin x. Why I will take a sin x common? So that I get the function of the form something plus something upon 1 minus something into something. Here the term must be 1, so that I can use the formula of tan a plus b. Okay, so once divide numerator and denominator by a sin x, I will get here 1, and after dividing here a sin x, sin will get cancelled, b by a, and here a will get cancel and we will get cot x. So b by a plus cot x upon 1 minus b by a cot x. So it is of the form x plus y upon 1 minus xy is tan inverse of b by a plus tan inverse of quat x. But this quat x I can write using tan x by Allied angle formula. Tan 90 minus theta is quat theta. So here this tan and this tan will get cancelled and you get pi by 2 minus x. So y is equal to tan inverse of b by a plus pi by 2 minus x. Now we'll differentiate this with respect to x. Tan inverse of b by a is a constant, derivative is 0. Pi by 2 is constant, its derivative is 0. Minus x, its derivative is 1. So we get dy by dx is minus 1. Now moving further, tan inverse of 5x plus 1 upon 3 minus x minus 6x square. Now here there is no 1, so we have to create 1 like this. Now I have directly written or expressed this 5x plus 1 upon 3 minus x minus 6x square as 3x plus 2 plus 2x minus 1 upon 1 minus 3x plus 2 into 2x minus 1. Now how it comes? As soon as I write 1, so here there will be plus 2. I will take the minus 1 from these three terms. So I get 6x square plus x minus 2 and I will factorize it. The factor will be 3x plus 2 and 2x minus 1. So if we take their addition, I will get 5x plus 1. By this way we can replace. Again I will use the property tan inverse of x plus y upon 1 minus xy is tan inverse of x plus tan inverse of y. Differentiate with respect to x, we get d by dx of the first function plus d by dx of the second function. Here I will use the formula tan inverse of f of x, that means chain rule. 1 upon 1 plus f of x square into d by dx of f dash of x. So the derivative of 3x plus 2 is nothing but 3. So 3 upon 1 plus 3x plus 2 bracket square, and the derivative of 2x minus 1 is 2 minus 0. So it's so we get here 2 upon 1 plus 2x minus 1 bracket square.